2D maps, and we'll look at the baker's map. And it's called that because it's a lot like that pastry map. So technically, the baker's map B is a map of the unit square onto itself. So by unit square, I mean x goes between 0 and 1. Also, y goes between 0 and 1. So we'll call this the square S. And the map, just like with 1D maps, there'll be this assignment of xn plus 1 and yn plus 1. So we'll do it this way. Xn plus 1, yn plus 1 equals, and we'll give two conditions. There's two things based on where you are in the x value. So if we are starting in the left half of x, so between 0 and a half, then this map will go xn plus 1 equals 2xn. So we'll get stretching, and then in the y direction, a times yn, where a is a parameter in the range greater than 0, but less than or equal to a half. For the other half, the right half of the square, and I'll give a picture. This is 2xn minus 1, a yn plus a half. So this is what it does. You could think of it as the product of two simpler transformations. To help figure out what's going on, we put this, well, it's a sad face because he's being chopped up. But we first flatten and stretch and then re-inject, right? And we re-inject so that the left half becomes now the bottom half, and the right half becomes the top half. So the map can be regarded as the product of two transformations that are basically flatten and stretch and then cut and stack. And the baker's map, this is called the baker's map, it exhibits sensitive dependence on initial conditions. So thanks to the stretching in the x direction, it has many chaotic orbits, uncountably many, in fact. Here we've illustrated for a less than a half. If a was equal to a half, then there wouldn't be any gaps. You notice there's these gaps that show up, and that's because we're just excluding them when we put things back. When it equals a half, we don't have any gaps. So this does have an attractor, and we can even try to construct what it is just based on these rules. So for a less than a half, Baker's map has an attractor. We'll call that A. That attracts all orbits, meaning you start with any initial condition, it's going to end up in this attractor. And the attractor is fractal. It'll be self-similar, and we could probably even calculate its dimension. So when we say that it attracts all orbits, that means if you start with some initial condition, the distance of the nth iterate of that point to the attractor converges to 0 as n goes to infinity. So how do we construct this attractor? Well, we start with S, and that includes all possible initial conditions. So S is the square. And then if we were to do images of S, so let's call this the first iterate of the Baker's map of S, A is less than a half, we'll have some rectangles and then repeat that. So take that and apply the Baker's map. And in each of these, we'll have, I think you can at least see where this is heading. Inside each of these regions, we'll have some additional regions. So that first image, B of S, consists of 2 strips of height A. Then that got flattened, stretched, cut, and stacked to yield B2S. So we have now 4 strips of height A squared. So each of these has the same height, and it's A squared. Oh, and notice that these 2 strips would fit inside the strip over here. B3S. This is gonna be hard to draw. I'm not even trying all that hard. But each of these, if we were to do this carefully, these are all strips of a to the 3 width. So this had 2 to the 1 strips of height A. This had 2 to the 2 strips of height A squared. This has 2 to the 3 strips of height A cubed. So I think you can imagine what the limiting set is. It's going to be a fractal. The limiting set A, we could just say B infinity S. Applying this infinite times. So what do we mean by limiting set? I want you to observe that the successive images of the square are all nested inside each other. So maybe I should draw this initially as yellow so you could get the idea. These are the initial conditions. So successive images of the square are all nested inside each other. One way that we could write that is Bn plus 1 of S is inside. It's a subset of Bns. It's like Russian dolls. I don't know if you've seen Russian dolls. I went to Poland and got them. So these are dolls, right? They're wooden dolls. I was enchanted by these when I was a kid because, right, you open it up and then there's a smaller one. It's like a smaller version inside with the same topology, and then inside another one. When you're a kid, you're like, where's this going to end? Oh, like, oh, what's going on? I think, does this one open? Oh my goodness. Yeah, it just keeps on going. Right. The good ones could have like 8 or more inside. This is, there's not much structure to this one, but they have all the similar topology. I'm going to get this confused. I'm going to try to put it back. When you keep repeating this, you're going to have something. Each iterate is inside another. And we're also going to have that A is a subset of Bns for all n. So this nesting property helps us to show that A attracts all orbits. We can visually see that it's a fractal. Maybe we could calculate the dimension. It's lines that kind of seem to fill an area. So it's going to be something between 1 and 2. So we could show that it's a fractal. It's also an attractor because the initial condition, any initial condition is going to have to be somewhere in the original square. And then it's going to move around. Right, I think this would go now down here. And then I forget what happens to it. You know, you could keep track of it. But it will be in that limiting set as you follow n goes to infinity. Take any point, any initial condition, Bn of that initial condition lies somewhere in one of the strips. So somewhere in one of those strips for any n. And all these strips are within a distance of a to the n of capital A. A is an attractor. And fractal. Well, let's verify the fractal thing. Let's see if we can count the dimension of it. There may be a way to do it like the self-similarity, but we could use a box counting dimension. And we're only doing this for a less than a half. Here is a sketch of the box. And just imagine this is the nth iterate. This is Bn of S. And there are boxes, right? Each of these strips has a width of a to the n. But if we think of boxes, here's a box. It's a to the n on both sides. A to the n that way. And it's a to the n that way. Now, if we were to cover the attractor with square boxes of size a to the n, how many do we need? We'll use the terminology of epsilon. Epsilon equals a to the n. Now, each of these strips has a length of 1. Each strip can be covered by how many boxes approximately? Each strip can be covered by, so if we have a length 1 and we're trying to cover this with boxes of size epsilon, this will be, 1 over epsilon, meaning a to the negative n boxes. And there are how many strips? There's 2 to the n strips. 2 to the n strips. With our box counting approach, how many boxes are there? The total number of boxes, n, which is approximately a to the negative n. That's the number of boxes for each strip times the number of strips, 2 to the n. And what does this give us? This gives us a over 2 to the negative n. So what's the dimension? The box counting dimension is if you can take this limit as epsilon goes to 0 of natural log of n over natural log of 1 minus epsilon. So then what is this? We could change our limit. The limit as epsilon goes to 0 is also the same as the limit as n goes to infinity of natural log a divided by 2 to the negative n over natural log of a to the negative n. And what does that give us? This will give us 1 plus natural log of 1/2 divided by natural log of A, which is going to be for A, greater than 0, less than 1/2. This is between 1 and 2, because this number over here will be positive. And that's what we expected. It's sort of like a bunch of lines that almost seem to fill an area, but maybe not quite. So D box goes to 2 as A goes to 1/2. And this makes sense because in some sense, the attractor fills an increasing portion of the square S as A goes to 1/2. This also illustrates the importance of dissipation. And this is dissipation in the sense of shrinking phase space volumes. One of the key things for the Lorentz attractor was that the volume was shrinking, and that led to an attractor. In mechanical systems where there is no energy dissipation and no damping, so like the orbital mechanics that I'm very familiar with, there's no dissipation. Phase space volume doesn't shrink, and there are no attractors. It's kind of surprising to people, but there are no you cannot get attractors in a conservative mechanical system. If you add some damping, then it's possible, but there's no like asymptotically stable points even in a mechanical system with just conservative forces. So you do need shrinking phase space volumes, and this holds even for something that's not related to physics at all. This Baker's map is kind of weird, but the phase space always shrinks, right? For A less than 1/2, the Baker's map shrinks areas in phase space. If you've got any region in the square, so here's our initial square, here's any region, call it R, then the area of the first iterate of R under the Baker's map is going to be less than the area of R. It's just going to shrink. So this just follows from geometry. The Baker's map elongates R by a factor of 2, then flattens it by a factor of A, and A is less than 1/2. So area of BR is going to be 2A times the area of R, and this is always less than 1. And we don't get an attractor if A equals 1/2. So if A is less than 1/2, we've got everything sort of shrinking down to a region that has no area, the attractor. For A equals 1/2, the Baker's map is area preserving. So the area of the iterate of any region is going to be the area of the original region. So the square is just mapped back onto itself. There's no gaps in between the strips. So this map has a qualitatively different dynamics. There's chaos, but there's no chaotic attractor. Transients never decay. The orbits just sort of shuffle endlessly around. So you could have chaos in a system like the solar system that doesn't have dissipation. Phase space volume stays the same, but it could get stretched and folded. It's getting stretched and folded in such a way that things never collect onto an attractor. Still have chaos, but no attractor. In fact, area preserving maps cannot have attractors. And this isn't just for 2D. If I had an n-dimensional map that preserved n-dimensional volumes, I wouldn't have an attractor. There'd be no attractor, but I could still have chaos. This is showing a fluid. So think of it as it's an area preserving fluid. We started with some color on top and another color on the bottom. And the interface between the two is basically what your eye is drawn to. You see a lot of stretching and folding. This is the idea of chaotic advection, which is a term due to Hassan Aref, who coined the term in the 80s, looking at two-dimensional fluid flows. But this is pretty standard in what you see. It looks like cream in coffee, but you get stretching and folding in fluids, often due to vorticity or other things. You could even see things like saddle points. Take your favorite phase portrait from earlier in the semester, and you'll see it somewhere in here. That's pretty cool. So you could have stretching and folding, even if you don't have dissipation, and get complicated dynamics. That's why the atmosphere, incompressible fluid, can show some amazing, interesting dynamics, as does the ocean. You can get dissipation, which means phase space volume shrinking. It can arise due to things like friction, if we're talking about a mechanical system, viscosity, damping. You can even introduce dissipation using control, but I think that goes way beyond what we're going to talk about here. Some classical areas that don't have dissipation, that are just conservative systems, are Hamiltonian systems that I've kind of hinted at before, and classical orbital mechanics and stuff. But there's other phenomena that arise in area preserving maps, and there just isn't time to go into it. So we're going to end here. We're going to talk next about another classic 2D map that generates chaos, the Hanon map, okay. Also from the 70s.